So, in the last module, we were in the middle of doing the derivation for viscous dissipation effect. That is, we wanted to calculate the temperature profile, expression for temperature profile, and hence the Nusselt number when viscous dissipation was considered. So, we had a simplified energy equation, and instead of going through the conventional way of substituting for velocity and directly integrating, we modified it a little bit by using a manipulation for the term, that is uz times dt by dr, which occurs uz times dt by dr, which occurs here as this one, and then this was my simplified equation. Substituted for duz by dr squared from here, mu by k remained, and then integrated this equation with respect to the area. So, in the r direction, so 2 pi r dr. So, we essentially took a ring of radius r and thickness dr. So, the area is 2 pi r dr. So, this was what was integrated from 0 to capital R. Okay. So, this was what was done, and we got to this step where we just set up the integral. Okay, we are now going to proceed further. So, left hand side is like this, right hand side, if you take the right hand side, you have, we will just do the terms separately. So, we are going to write 1 by r integral 0 to capital R, 1 by r d by dr of r dt by dr 2 pi r dr. R cancels with r, therefore, you get what is 2 pi times integral 0 to r d by dr of r dt by dr with respect to r. What does this mean? Integral and differential. So, what you get is nothing but 2 pi r dt by dr, r dt by dr, which is going to be evaluated at capital R, minus r dt by dr, which is going to be evaluated at the center line, r equal to 0. Now, r equal to 0 is, when you substitute here, automatically this term goes to 0. Otherwise, also dt by dr at r equal to 0, which represents the location of maxima or minima, would make this 0. So, both these are 0. So, this term is identically equal to 0. What is r dt by dr at capital R? That is nothing but, so if you look at the geometry, q double prime is equal to minus k dt by dy, or this is k times dt by dr at r equal to capital R. Why? Because the coordinate system is such that if this is the center line, this is my r, this is my y, q double prime is, so this is my coordinate axis is reversed this way, you have the minus sign which is lost. So, dt by dr, which is occurring here at r equal to capital R, is nothing but q double prime divided by k. Therefore, this term, if I just write it here, this term is now going to be 2 pi as it is. R evaluated at capital R would be simply capital R. dt by dr at capital R is nothing but q double prime by k. So, this term, right hand side integrand, this integrand becomes this quantity. So, this integrand becomes this quantity. So, 1 by r d by dr of r dt by dr 2 pi r dr integral 0 to capital R ends up being this term. Second term on the right hand side, this is the first term. The second term on the right hand side, 16 um bar squared mu by k capital R to the power 4 integral 0 to r 2 pi r cubed dr is nothing but 2 into 16, 32 pi u m bar squared mu by k r to the power 4 integral of r cubed is r to the power 4 is nothing but r to the power 4. So, this is capital R to the power 4 divided by 4 when you supply the limits. So, R to the power 4 by 4, when you substitute the limit, it is capital R to the power 4. What happens? 4 ones are 4, 4 8s are 32, capital R to the power 4 cancels here, and you are left with 8 mu pi u m bar squared divided by k. This is my second term on the right hand side. The first term on the right hand side was this, the second term on the right hand side is this. Now, left hand side, we will manipulate the left hand side now. Now, consider the left hand side of the energy equation. So, let us write the left hand side, that is 1 by alpha 0 to capital R, 1 by alpha 0 to capital R d by dz of t u z 2 pi r dr. This is nothing but 2 pi by alpha, and I am going to write this in this form, u z of r times t of r comma z r dr. Just to emphasize to you that u z is a function of r, t is a function of r comma z, and that is why we have to have this integral. Now, let us recall. Let us recall the definition of bulk mean temperature. Bulk mean temperature Tm bar. What is the definition? The bulk mean temperature was obtained by energy balance. Rho A U bulk mean times Cp times T bulk mean is nothing but integral 0 to capital R rho u of r Cp T of r comma z dA, which is 2 pi r dr. So, if I cancel rho and Cp and pi, rho Cp and pi, I am left with u bulk mean Tm capital R squared by 2 is equal to 0 to capital R, R u of r, T of r comma z dr. And what is this? This is nothing but your left hand side of the equation with that 2 pi by alpha sticking there. So, this step will help us manipulate the left hand side of the energy equation as 2 pi by alpha times u m bar T m bar capital R square by 2, which becomes equal to pi into R squared by alpha d by dz of this quantity. Sorry, I forgot the derivative here. So, 2 pi by alpha times derivative of this quantity. Somehow I missed the derivative here, sorry about that, d by dz. So, d by dz of this quantity. So, this is going to be 2 pi by alpha u m bar r squared by 2 u m bar r squared by 2 d by dz of bulk mean temperature. So, 2 would cancel, and therefore, left hand side would become equal to pi by alpha u m bar r squared d by dz of bulk mean temperature bulk mean temperature is only a function of Z. Why? Because I'm having the profile which is changing only this way, thermally fully developed. T is a function of Z only. T bulk mean is a function of Z only. Why? Because you have already integrated with respect to R. Therefore, the R dependency is completely lost. So, d by dz of T bulk mean becomes equal to dt m by dz. This fact is important, and then this is my temperature profile. Local profile is a function of R and Z, but bulk mean is only a function of Z. Therefore, the left hand side of the energy equation now becomes like this. Now, I substitute for the left hand side and right hand side. Simplified energy equation becomes, left hand side is pi by alpha u m bar capital R square divided times dt m by dz. Right hand side I had two terms, that is this one and this one. It is 2 pi r q w by k plus 8 mu pi u m bar squared by k. This is exactly what we did in our derivation for laminar flow through pipe constant wall heat flux. So, this is my simplified equation. I just want dt m by dz. So, I divide through by this quantity everywhere and also use alpha is equal to k by rho Cp. So, use this and divide through by this quantity, left hand side quantity. So, I get dt m by dz is equal to 2 pi capital R by k times alpha by pi u m bar R squared q w plus 8 mu pi u m bar squared by k divided by this. So, you are going to have alpha by pi R squared u m bar as it is. So, alpha is k by rho Cp. So, you get 2 pi R by k, k by rho Cp 1 by pi u m bar R squared q w plus 8 mu pi u m bar squared by k, k by rho Cp pi R squared u m. So, when you just cancel the terms pi, pi, r, r, k, k, you are left with 2 q double prime divided by rho Cp r u m bar plus, here you cancel off k, you cancel off 1 u m, pi cancels. So, you get 8 mu u m bar divided by rho Cp capital R square. This is my dt m by dz. This is my ordinary differential equation for the temperature variation. We had only this term before. This term is due to viscous dissipation. This term was originally there. This is the additional term that we have got, and now the procedure is identical. So, you substitute now for all these things. So, you want to get the energy equation in a form that we like. So, what was my expression? So, 2 dt m by dz was there. So, dt m by dz we are just going to use directly. So, I am going to start this. Just go back here. So, you have this step, energy equation I substituted here, remember. So, when I substituted this, I am now going to go back to dt by dz is equal to dt m by dz. That is why I have done all this manipulation. all this manipulation for that. So, I substitute dTm by dz in 2 um by alpha 1 minus r by capital R squared dt by dz equal to 1 by r d by dr or dt by dr plus 16 bar squared by r to the power 4 mu by k small r squared. So, when I substitute this substitution is going to be done, and um1 by r blah blah blah. So, this one is only a function of r. If you can see, this is only a function of r, because was a sorry, it's only a function of z. Sorry, this is only a function of z, because is a function of z. These are all constants with respect to z. This also is only a function of z. So, this whole quantity. So, when I substitute this, I would get 2 bar by alpha 1 minus r by r squared, this one bracket 2q by rho Cp r plus 8 mu bar by rho Cp r squared is equal to 1 by r d by dr of r dt by dr plus 16 bar squared mu r squared by k r to the power 4. This one is a function of z only. This is a function of z only. Therefore, this one becomes d by dr. This is a function of r only. Sorry, this is only a function of r. This is also a function of r. Therefore, this becomes d by dr. So, everything here is a function of r. Therefore, I get d by dr as a regular derivative, and then I separate the variables. So, I am just going to write here dt by dr is equal to, so I integrate once. So, I get dt by dr is equal to 4 bar by k q double prime by bar r plus 4 mu bar by capital R squared into r by 2 minus r cube by 4 capital R squared minus 4 bar squared mu by k r to the power 4 plus C1 by r. Integrate again, you get T of r. This is 4 bar by k q double prime over r plus 4 mu bar by r squared times r squared by 4 minus r to the power 4 by 16 r squared minus mu bar squared by k r to the power 4 capital small r to the power 4 C1 log r plus C2. This is my temperature distribution. You have to do the maths to get it. Now, have a boundary condition at r equal to 0, dt by dr equal to 0 implies C1 equal to 0, just as before, and then r equal to capital R, t equal to t wall, you get C2, an expression for C2. Once you get that, then what you need to do is, this can be integrated now to get the bulk. You got T of R as a, then you substitute for C1 and C2, So, C2 would be nothing but T wall minus all this quantity evaluated at R equal to capital R. Substitute for C1 and C2, get T bulk mean by integration as 1 by pi r squared 0 to r t of r comma z u of r dr, and once you do the maths, this is a lot of maths here like before, you get T wall minus Tm is equal to 11 by 48 q double prime d by k plus mu um bar squared by k. This is 48 by 11 which came before, as Nusselt number is equal to 4.36. What is additional is now only this part. This is slide 7. We'll do slide 8 here. The additional part is this term, and once you simplify this, you are going to get Nusselt number is equal to q double prime d by k t wall minus tm, which comes out to be 1 over 11 by 48 plus mu um bar squared by q double prime d. This quantity is called as the Brinkman number. Therefore, I get Nusselt number is equal to 48 by 11 plus 48 times Brinkman number, where Brinkman number is nothing but mu um bar squared by q double prime d. So, you see here very quickly that as viscosity effect increases, Brinkman number increases. As Br increases, Nusselt number decreases. As Br tends to infinity, Nusselt number tends to 0. In the limiting case, when Br is equal to 0, Nusselt number is equal to 48 by 11, which is 4.36. So, this completes the effect of viscous dissipation. We have rushed through the maths here, which I have left as an exercise. However, you can do this. The important parts have been highlighted, and you see that this can be a very useful exercise to understand the effect of viscous dissipation. Usually we neglect it. It will be good to check this quantity and see if it is small, and therefore see the effect of Brinkman number on Nusselt number. Thank you.